section 7.2, continuing in chapter 7, which is quote unquote analytic trigonometry. So we're still building up to solving trig equations, right? We talked about identities last time, identities, and that was a fair bit of fun, right? Just verifying identities and stuff. But maybe hard to motivate, like the whole, I'll be honest with you, the whole verifying identities thing. Here's how my experience being a mathematician, having gone through the calculus sequence and other classes, like other applied math classes, differential equations, partial differential equations. I don't have a lot of experience in applied math, but the little that I do, you don't ever really verify identities. Okay, that's really just purely an exercise we do in trig class to make sure that, for one, that you understand the identities, and for two, just to make sure your algebra is on point, right? Your fraction, arithmetic type stuff, you know, common denominator stuff when the fractions look all crazy with trig functions in there. But now we're getting to some things that really will be used. Oh, and that's not to say the identities aren't used. The identities in 7.1 are used all the time, but the actual exercises or examples we did of verifying the identities, those weird identities I gave you and asked you to verify, and I did as examples, that's not done very often outside of just trig class. But the Pythagorean identities and reciprocal identities and cofunction identities, those are all used all the time. All right, so, and now we're moving into another set of identities here. Moving into another set of identities that we're going to call the addition and subtraction formulas for sine, cosine, and tangent. So what we have here is if we have sine of some input that can be written as a sum, either it's given as a sum like this, or we can write it as a sum, then that's going to be equal to sine of the initial input s. And why are we using s and t? Well, that's just, I'm just following. Again, I'm trying to be a good instructor by following along with what the text is using, since that's what we're using for homework and exams. Those problems are pulled from the text, so trying to follow the notation the text is using. Okay, so here we go. Let me discuss this formula a little bit more. So we have two inputs, two angle inputs here. They're different. They don't have to be different, but in this case, they're, you know, in general, they could be different. And we're taking a sum inside the sine function. Then that can be explicitly written out in this way, with the sine of the first input times the cosine of the second input, and then over here, cosine of the first input, sine of the second input, and then taking the sum of those two products there. Now, what if I say, what about the difference, sine of s minus t? That's the same as, well, it's really nice how it works because of the way, and whoops, that's going to be minus. I can show you this in detail. Well, I'm actually not going to derive them, but the reason this one is so nice and clean and literally all that changes is that plus sign changes to a difference right there, a minus sign there. It's coming from the fact that sine is an odd function. That's what's going on here. All right. Then we have cosine of s plus t. So very similar formula coming here, but we should be careful. It's not exactly the same. For cosine of a sum of two inputs here, we have cosine of the first input times cosine of the second input. So notice the difference there. Up here it goes sine, cosine, cosine, sine. Down here it's going to go cosine, cosine, and then sine, sine. It's very different. The things being multiplied it's different here. All right, and then cosine of s minus t. Again, just the sign changing here. Oh, dang it, I did it again with this is minus right here. This first one is minus, sorry. There we go. Okay. All right, so the first one, if it's a sum inside the cosine function, then the two products here should be attached by a minus sign. Okay, so it's a little opposite. It's coming down to the fact that, well, okay, I'm saying it's coming down to the fact that, you know, the functions are even or odd. What I mean is, if you want to build the difference functions from the sum formulas, then you'll use that idea that sine is an odd function and cosine is an even function. That'll be in there. Now, how do you actually derive the formulas just from scratch, though? Like, assuming you don't know the formulas, how would you derive them? And the book walks through a nice little derivation graphically. I'm not going to, well, actually, they do it graphically and algebraically, I think. And a picture is just a really nice way to show what's going on here. I'm not going to walk through that because I'm not going to hold you responsible for it. You know, if we were in like a in-person class, I might make a little exercise out of it that we all do together. But really, to be honest, I mean, what would happen if I derive them for you? If I tell you that I'm not going to make you responsible for knowing how to derive these, then you would just probably skip through. You would just slide right through that part of the video. So I'm not going to do it, but I am going to tell you the formulas for tangent. So for a sum inside of a tangent, that's s plus t inside of a tangent, two different angles, s plus t. Or they could be the same. This formula is generic that way. The tangent function, or the tangent formula, is going to look quite different. There's that one. So it's tangent of the first input plus tangent of the second. And the first part of the sum over here, tangent of the first part plus tangent of the second part, all over 1 minus the products of those two tangents. And then tangent of s minus t, so here comes the difference function. And all that's going to happen is the signs change. This becomes a difference on top. And we get a sum in the denominator. But they look very similar. So here's what you should do. You should commit these to memory. Make some flashcards and commit them to memory. By the way, they all are, if you do have our physical copy of our textbook, which you might, because you might have bought it for 112 in the past. And any good trigonometry or pre-calculus algebra and trigonometry text or calculus text, is all sorts of math textbooks are going to have the trig identities and formulas in their front cover. Well, I say that and then it's not here. Maybe it's in the back cover. There they are. There they are. Oh, they even got graphs of trig functions here too. So this is a nice reference in the back of the book. You can find this in the ebook too. I'm sure it's all the way at the back of the ebook. But here we have, this is what we're looking at right here, addition and subtraction formulas. Those are the 6 formulas I just wrote down. Ugh. Let's see, let's go find it in the ebook together, just so that I know that you know where it is. So I'm actually in the ebook right now. So let's see, where do I want to go? Oh, how do I get there? Let's see. Let me close this. Full book. Over here on the right, full book. I want to go to the very end. Let's see if I can just. Oh. Oh, this is just. There we go. Table of contents. There we go. Formulas and definitions all the way at the end. Formulas and definitions. There's all the stuff we need. Fundamental identities. There's got to be a way to do it here, though. There's got to be a way to do it here. Opens. Oh, man, are you kidding me? Well, I'm glad I went and tried to look for this, because what a nightmare this is. Oh, you can make flashcards. That's kind of cool. All right, let's see. Oh my God, just let me get back to the main book. Oh, well, I guess that's how you have to do it. You have to click this little full book button and then go to table of contents and go all the way down to formulas and definitions. And then you got to know what you're looking for. So if I want to look for the addition and subtraction formulas, I click that and there they are. And then I think I can just navigate from here. There's other formulas that we're gonna look at, talk about. Here's the cofunction identities and the fundamental, so-called fundamental. So this is like reciprocal identities and the Pythagorean identities here. And it's cut off. Wow. You know, ebooks. Sometimes they're such a delight to work with. There's a way to get this page here. I think what I'd have to do is close this and reopen the ebook, and so that it would drop me back onto like the very front where I'm in the full table of contents. But since I don't want to have to log back into WebAssign and reopen the ebook and all that, so I'm not going to do that, but I'm sure that that's what I would have to do. All right, so let's talk about using these identities. So let me get back to what I was doing. Again, there is derivations for these in the text that I'm skipping over. All right, so I'd like to follow the examples in the text just for your convenience too, not just my own. Well, I'm also probably going to do some homework assignments or homework problems that I assigned in WebAssign, because I gave a lot of these addition and subtraction formula problems. Find the exact value of each expression. Okay. Recall that exact value means do not plug into a calculator, right? Exact value means that we want to have it written down as a nice, clean, compact answer, like probably a fraction of like radicals or something like that. But the problem is this 75 degrees is not one of our common angles. Our common angles that we know in degrees, which we haven't thought about those in a while, but the common ones we know about are 0, 30, 45, 60, 90. That's what they are in the first quadrant, and then other versions of these. So 120 in the second quadrant, 120. 135. And then 160, 180, 150, 180. These are the ones in the second quadrant. And then in the third quadrant, et cetera, et cetera. Do I need to list? No, I don't need to list all of them. All right. So the point is, what am I going to do here? The point is I need to find a way to write 75 degrees as the sum or difference of two of these angles. Okay, so what two angles do you see that I could use to build 75 from this list of things that I know about? How about 30 plus 45. So why do I need to do that? Well, because now I can say cosine of 75 degrees, which is normally something that I could not write an exact expression down for, an exact value. Prior to the techniques that we're going to learn in this section, how would you have dealt with this? The best you could have done is plugged it into the calculator and then given me an approximate answer, like rounding whatever the calculator gives you. But now watch, But now watch this. We can say cosine of 75 degrees is the same as just split that 75 up inside the parentheses. And then recalling our formula for the sum inside of a cosine, we say this is the same as cosine of 30 degrees times cosine of 45 degrees minus sine of 30 degrees times sine of 45 degrees. Now we've been thinking about radians for so long, maybe you would like to say, okay, I totally forgot what these are as radians, so maybe it'll be helpful, like if I write these down just as a reminder. 30 degrees is pi on 6. 45 degrees is pi on 4. There they are in radian mode, or radian form, the angles in radian form. Now we need to think about, what does each of these evaluate to? What does each of these evaluate to? So I need my little reference triangles, and I'll just draw them using degrees. Okay, so a 30, 60, 90, where there's the 30-degree angle. This side's going to be square root of 3. This side's going to be 1. That's going to be 2. I'll use that for the two 30-degree angle inputs. And then I've got a 45-degree, 45, 45, 90. And those sides are square root of 2 for the legs and 2 for the hypotenuse. All right. That's going to be a helpful reference here, because my first... Oh, and by the way, if you like this radian form better, then you can draw these angles. Instead of 30 degrees, you can put pi on 6 in there. Instead of 45 degrees, you can put pi on 4 in there. Okay. Cosine of 30 degrees is adjacent over hypotenuse, right? Adjacent over hypotenuse, so I'm getting square root of 3 over 2. I'm putting a little dot for times, and now I'm going to find cosine of 45 degrees. That's going to be square root of 2 over 2. See how I'm doing this? That, then my minus sign. Sine of 30 degrees, so I'm looking at this triangle. Sine of 30 degrees is going to be opposite over hypotenuse, so 1 over 2 times, now I'm going to look at this term, square root of 2 over 2. Okay, now I just need to clean this up. Square root of 3 times square root of 2 is square root of 6, and then over 4, right? 2 times 2 in the bottom. On the right-hand term, I have square root of 2 over 4. Then finally, I'm getting square root of 6 minus square root of 2 all over 4. And that's as far as I can go, right? I cannot subtract these because they're not like terms. Well, yeah, that's one way to say it, but that's fine. That's fine. And this is as far as we can go. So that is the point of these sum formulas. These formulas that let you take some angle that you may not be able to deal with and pull it apart as a sum or a difference, and then from there the way you pull it apart should come from angles you actually do know about, and then from there you just follow through the formula. So could I have written this as a difference of two angles? Yes, I could have used, here's a good thing for you to try. Note that cosine of 75 degrees is the same as cosine of 135, which is from my list, minus 60. So you should try that and see what you get. You should end up getting, you will, if you do it correctly, you'll end up getting the exact same answer. You may have to manipulate it a little bit to get it to look the same. There might be a minus sign it might be flipped around or something, but this should yield the exact same thing. You got to keep in mind that the cosine of 135 is in the second quadrant. So when you do that, that one should yield a negative. Like a negative square root of 2 over 2. Oh, excuse me. All right, let's do part B. So this is opening up a lot of possibilities for us. A lot of possibilities for us because now we can deal with not just our special angles, but any sums or differences of our special angles. What are our special angles as in radian form? Well, you've got 0, you've got pi on 6, pi on 4, pi on 3, pi on 2. Those are the ones in the first quadrant. Well, this is on the axis, right? So anyways, these three, this is x-axis, and then these three in the first quadrant, and then that's the positive y-axis, and then I could go into the second quadrant, but, well, okay, sure. Since I did the first two quadrants for the previous one, I'll write them down here as well. So past pi on 2, we're going to have, got to think about it, let's see, 3, 4, 2, 3, 4. Anyways, 2 pi on 3, and then 3 pi on 4. Oh, excuse me. And then 5 pi on 6, and then pi. All right. Need to find some combination of these that gives me pi on 12. And I probably need to find a difference, right? Because all of these are bigger than pi on 12, so I'm not going to be able to add 2 of them to get pi on 12. So I need to find a difference of 2 of these. So what does this mean? Your fraction arithmetic has to be on point here. You've got to know that if you take pi on 3 minus pi on 4, like a third minus a fourth, that you will get pi on 12. Because if I get a common denominator here, that's what it'll look like with a common denominator, and then of course that just leaves me with pi on 12. Your fraction arithmetic has got to be on point. What do you do if you're completely lost and you don't know what? Just start trying some subtraction. Do like pi on 2 minus pi on 6 and see what you get. Pi on 2 minus pi on 4, see what you get. Just start bouncing around, and eventually you'll be able to figure out, like, you'll get closer and closer to what you actually need, which is pi on 3 minus pi on 4. So I'm going to say cosine of pi on 12 is the same as cosine of pi on 3 minus pi on 4. But that's the same, according to my formula, as cosine of that first term times cosine of the second term. And then recall that it's plus, because the cosine formula is a bit weird. For cosine of a difference, we have plus in the middle. And then the sine of those two angles, sine of pi on 3 times sine of pi on 4. Do you recall what a pi on 3 angle looks like? I mean, what a pi on 3 triangle looks like, right? Because we're going to need that. I already know the pi on 4, that's the 45-degree angles. These are both going to give me a root 2 over 2. So I know that one, but what about the, if this is a pi on 3, then this side is square root of 3, this side's 1, that's 2. I need that as reference for this and this. Cosine of pi on 3 is adjacent over hypotenuse, so that's 1 over 2. I already know cosine of pi on 4, the previous problem, that's like the 45-degree one, so I already know that's square root of 2 over 2. I'm going to have plus sine of pi on 3 is opposite over hypotenuse. and then times sine of pi on 4 is the same as cosine of pi on 4, so giving me another square root of 2 over 2. Clean this up. Oof, that's a 6. And just rewrite it. Cleans up very similar to the previous problem. All right, very similar. And no, you cannot add the 2 and the 6, right? This is as far as you can go. You cannot stuff them under one radical and add them together or anything like that. This is as far as we can go here. Okay. Now, we're going to go in reverse, but first I want to go find some problems from the homework that are similar to this first example. So give me 1 second to log in to WebAssign. I'm just going to continue example 1, just call this part C. Okay. Let's do tangent of 75 degrees. Well, I can actually pull it apart the same way. 75, as I did part A. 75 degrees can be written as 30 plus 45. So that means tangent of 75 degrees is the same as tangent of 30 degrees plus 4. So this first step, all I'm doing is tearing apart that angle, right? Now is when I apply the identity or the formula, which is this nightmare, right? So hopefully, you should have that written down for reference. So I'm going to have tangent of that initial input there, then plus tangent of the second over 1 minus, and then the product of them. And then the product of them, tangent of 30 degrees times tangent. So I got to find what these are. In fact, since this formula is a little bit more complicated, it just looks a little bit worse here. How about I go off on the side and figure out what tangent of 30 and tangent of 45 are? First, I need the reference triangles, right? So I'll draw my 30, 60, 90 here. There's 30 degrees. This side is square root of 3. This side's 1, that's 2. And my 45, 45, 90. Square root of 2, square root of 2, and 2. All right, so tangent of 30 degrees. So I'm writing these off on the side, unlike part A and B, because the formulas aren't quite as complicated for sums and differences of sines and cosines, but for tangent, it's a bit more involved. So maybe it's helpful to put this on the side. Tangent is opposite over hypotenuse, so that's giving me 1 over square root of 3, which I also know can be written as square root of 3 over 3 if I want to rationalize the denominator. That's probably what I'll use. Probably use this, okay, square root of 3 over 3. Now tangent of 45 degrees is going to be opposite over adjacent. That's square root of 2 over 2. Square root of 2 over square root of 2. That's just 1. That's nice. That's nice. Just a 1 there. So up top, tangent of 30, let me draw my fraction bar. There we go. Now up top, tangent of 30 degrees is giving me square root of 3 over 3. And plus, then tangent of 45 is 1. And down in the bottom, I have a 1 minus square root of 3 over 3. I'll wrap it in parentheses just to emphasize, and then times 1. Okay. So I'm getting now, let me write it here. Square root of 3 over 3 plus 1 over 1 minus square root of 3 over 3. Now at this point, this can definitely be cleaned up. Will WebAssign accept this? I'm actually not sure. The answer they're showing in my, because I can obviously I can see the solutions here and what I'm looking at. The solution they're showing is much more cleaned up. I think that if you typed in this answer, I think it would accept this. I think it would. But just in case, I'm going to show you how you would clean something like this up. Okay. Get ready because it's gonna go a little crazy here, but it's not too bad. First thing I'm gonna do is I'm gonna get a common denominator in the top and in the bottom, and that denominator is gonna be 3. So first of all, here's my big fraction bar, the central fraction bar. Now in the top, I'm gonna have square root of 3 plus 3 over 3. So I just got a common denominator of 3. A 1 is easy to get a common denominator with. It's just 3 over 3, right? And then I push the fractions together. I'm going to do the same in the bottom. Okay, just getting common denominators there and then pushing the fractions together. My next step, I'm going to say, well, this is the same as square root of 3 plus 3 all over 3 times the reciprocal of this, right? Fraction division. So 3 over 3 minus square root of 3. And then notice that the 3's cancel, so I've got square root of 3 plus 3 over 3 minus square root of 3, which does not cancel, these 3's canceled, but this will not cancel, like as much as you may want it to, this will not cancel. What I have to do now, and I'm going to rewrite it, if I really want to keep cleaning this up, I've got to multiply by the conjugate, if you recall that. The conjugate of that denominator, because now what I'm doing is I'm trying to rationalize the denominator. Yeah, sometimes cleaning the answer up is like more work than setting up and solving the identity, right? All right, so in the bottom here, it's a difference of squares. I'm going to shorten this up. I'm going to say this is going to be the same as 9 minus 3, which will end up being 6, of course. In the top, I'm going to have 9 plus 6 square roots of 3 plus 3. Okay, I'm going to just trust that you can multiply, using the distribution for a 2 by 2 in the top and a 2 by 2 in the bottom. I'm trusting that you can replicate that. And that's going to give me 12 plus 6 square roots of 3 all over 6. 9 minus 3, right? 9 plus 3 in the top, giving me the 12. And then I can factor a 6 out of the numerator, giving me 2 plus square root of 3 all over 6, like that. So you just pulled a 6 off of the 12 and the 6 square root of 3. Finally, those 6's cancel, and I get this nice little compact thing, 2 plus square root of 3. That's quite an adventure there to get this thing to look like this. And I'll be honest, I skipped a lot of details there, and it still took a full page here. So hopefully WebAssign will take this. Just let me know if you run across a problem where WebAssign is not taking the answer. First of all, make sure you're plugging it in correctly. Make sure you got your minus signs in the right place and everything. And then if it's not taking it though, and you're trying to clean it up, and the algebra in between is just kind of messing you up, just let me know. Let me know, and we can deal with that on a case-by-case basis. Shouldn't be too many problems. It's really the tangent functions. That's the one that introduces that the denominator. That's where things are going to get a little wild. Let's look at this one now. So I'm still in example 1. I want to do a few of these. So this is part D. Sine of 43 pi over 12. how can we deal with this? Probably be helpful to get rid of any extra revolutions. Remember that an extra revolution is like a whole extra 2 pi or 360 degrees, but in this case, since it's written in radians, 2 pi is a full revolution. If I give you an angle that's like at pi on 6, but I say, oh, it's 2 pi plus pi on 6, then you would say, well, that extra revolution is not necessary, right? So we've talked about these before. We're getting rid of extra full revolutions because it doesn't change where your angle ends up if you're adding an entire full revolution. Is there a full revolution in this? Well, yes, because what does 2 pi look like with a denominator of 12? I'm trying to get a 2 pi out of this. Can I pull a 2 pi out of this? Yes, because 24 pi over 12 is 2 pi, right? And then what's left over here? (19 pi over 12), because I know 24 plus 19 is 43. So what I really want to work with is I don't need this. This is extra. That's an extra revolution that I don't need. So what I really want to work with, is sine of 19 pi over 12. Now I still need to figure out how to find two angles. So by the way, what am I saying? I'm saying this is equivalent to this by getting rid of that extra revolution that was inside that angle. So this is equivalent to this. But I still need to tear apart this 19 pi over 12 because, you know, this is not some recognizable angle. I need to figure out from that list I gave you, or the angles that you know in radians. Here are the first two quadrants. How can I write 19 pi over 12 as a sum or difference? Here's a good technique. Maybe you can pull the 19 apart, like leave the denominator of 12. Maybe I'll just assume it can be written as a sum here. Leave the denominator of 12 and try to pull 19 apart so that the two fractions, they'll simplify to a nice like pi on 6, pi on 4, or pi on 3, or pi on 2 type angle. So what if I said, like, what's a nice number I could pick? Like, how could I pull apart 19? And there's going to be more than one answer, by the way. How about I try 16 and 3? Well, 16 over 12 is the same as 4 pi over 3. That's good. That's one of my special angles. And 3 pi over 12 is the same as pi over 4. Good. This is going to do it. This is going to be just fine for me. Give me one moment. Okay. So where are we at? Let me get us caught up here with where we're actually at. We've got that sine from the original problem, 43 pi over 12 is the same as sine of 19 pi over 12 by getting rid of that extra revolution, the extra 2 pi, which in terms of a denominator of 12 is the same as 24 pi over 12. Got rid of that. And now we said also, by the way, you can write sine of 19 pi over 12 as 16 pi over sine of 16 pi over 12 plus 3 pi over 12, which by the way is equal to sine of 4 pi over 3 plus pi over 4. Those are special angles. Before I go decide, I'm going to draw my reference triangles and everything just like normal, but let me go ahead and get the formula down. It's going to be, for a sum, sine of 4 pi on 3 times cosine of the second angle, and then plus, cosine of the 4 pi on 3 sine of pi on 4. I'm going to rewrite it. I'm going to rewrite it down here. Sometimes I don't notice the edge of my paper because it's the same as my background here. So I don't notice it until I'm right there at the edge. Okay, there we go. Now I'm going to need to know what sine of 4 pi on 3 is, and cosine of 4 pi on 3, and also cosine of pi on 4 and sine of pi on 4. Luckily, I already know these, right? It's going to be square root of 2 over 2. Both of these, the pi on 4 ones, square root of 2 over 2. What about these guys? All right, so 4 pi on 3, that's down in the, which quadrant is that in? That's below pi, so it's in the third quadrant. So both of these should end up being negative. Okay, so make sure you note that 4 pi on 3 is in third quadrant. So cosine and sine will be negative. What kind of reference triangle do I use? Well, it's a pi on 3 reference triangle, because that's the reference angle for 4 pi on 3. Pi on 3, that's a 1, that's a square root of 3, and that's a 2. All right, now I'm ready to fill this in. I'm going to change the colors just to have a little bit of contrast here. So sine of 4 pi on 3, opposite over hypotenuse, so square root of 3 over 2, but recalling that it should be negative because it's in quadrant 3. And then cosine of pi on 4, well, cosine of pi on 4 is square root of 2 over 2. Okay. Now plus cosine of 4 pi on 3, that's going to be adjacent over hypotenuse, but it is negative. So since it's negative, how about I wrap it in parentheses? In fact, I can wrap all 4 of them in parentheses. Here comes the last one, sine of pi on 4, square root of 2 over 2. All right. Fraction multiplication, negative square root of 6 coming from square root of 3 times square root of 2 over 4, minus square root of 2 over 4. Can be written a few different ways. You can write it like, whoops, square root of 6 minus square root of 2 all over 4. Or you could write it with a minus sign stuck on the very outside of the fraction, which implies that both terms are negative. If you do that, then the sign in the center, so it's implying that when you put this back that it would negate both terms, so you need a plus sign there in the center. In fact, if I go look at what WebAssign did, yeah, this is how WebAssign wrote it as their solution, but this is fine too. This is fine, but it's a big difference. Putting the negative out here next to the left of the fraction bar implies that both of these are negative. So if you want to do it that way, you've got to make sure you put a little plus sign in here instead of a minus sign. If you stuff the negative up in the numerator, then you just leave it as it was, negative square root of 6 minus square root of 2. These are the same. Either one is fine. But you know what's not fine is a combination, right? You cannot do this where you have the negative on the outside. Like this is what a lot of students will try to say, right? Put the negative on the outside and negate the 2 in there. This is false. This would be something different. This would be the same as having the 6 being negative, but the 2 actually being positive. Because this negative implies that you're negating both of these. So this is one of these is what you want here. All right. I think that's enough for that kind of problem. Let's go on to example 2. Again, find the exact value, but this time we're going to be using the formulas in reverse. Why not? Just for practice. Never really found that I've used them in reverse in my experience, but it's still a good exercise. Definitely use them as they're intended, like all the examples we just did, but using them in reverse, I've never really seen that come up. I don't know if it would ever, I mean, I'm sure it does somewhere, but at the very least, it comes up right here in trig class. All right, so we recognize this as how do we solve this? First, we have to recognize, so we're going in reverse. I've given you the output of the formula and asked for you to clean it up a bit. Recognize this as a sine of s plus t, where s is equal to 20 degrees and t is equal to 40 degrees. And how do I find that out? How do I recognize that? I just have to look at how this is structured. It goes sine, cosine, plus cosine, sine. That's going to line up here, sine, cosine, plus cosine, sine, and then just lining up what s and t are. So we have sine of 20 degrees. This whole thing is equal to sine of 20 degrees plus 40 degrees, but that's just the same as sine of 60 degrees. And look, that's one of our nice angles. That's just a 60-degree angle. I'll quickly draw my reference triangle, even though we've already done one of these today, but there it is. And that's going to give me square root of 3/2. So what's the point of this problem? It's just more practice using the formula, just practicing it in reverse. That's all. Like, why would you ever pull apart sine of 60 when it's already such a clean answer? Why would you ever want to write it like this? I don't really know. I honestly think it's just, this really, to me, is just more practice getting familiar with the formulas. That's all this is. I've given you another similar one to that in the homework. Let's see, what else have we got here? I'm just looking through. I'm trying to make sure I don't want to go. We're not doing all of the section 7.2. We're not doing the last bit of it, so I'm just making sure. Is this what I want to go over? Yeah, why not? Let's do this. Just as another practice using these formulas, these new formulas, prove the cofunction identity cosine of pi over 2 minus u is equal to sine. So remember that from section 7.1, cofunction identity. What do I mean prove it? Well, you have a formula that tells you how to deal with the difference inside of a cosine function. So I know by that formula, period there, and then I have that cosine of pi on 2 minus u is equal to cosine of pi over 2 times cosine of u plus, and then the product of the sine at those two values, sine and sine of u. Okay, so what does this do? Well, what is cosine of pi on 2? So remember, cosine is an x value. Pi on 2 is up on the positive y-axis. What's the x value on the y-axis? It's 0. Since this is 0, this whole term just goes to 0. What's sine at pi on 2? The y value on the y-axis on the unit circle is a 1. So this is just 1. So this whole term goes away because 0 times cosine of u, it just zeroes out, leaving me with just this term. But this little term right here goes to 1. So it basically, this disappears, leaving me with just sine of u. There it is. Easy as that. That's how we can verify this cofunction identity using the addition and subtraction formulas. And you could do this for any of the cofunction identities. Probably wouldn't be quite as fun for tangent. In fact, tangent's not defined at pi on 2, so that wouldn't work anyways. But yeah, that's how you can prove at least the sine and cosine cofunction identities. Okay, I believe that's going to be it for 7.2. Let me just glance through the homework one more time. Make sure. That's all I want to go over for this section. All right, that is it for 7.2.